Hey everyone, it's Justin again. Through everything we've learned about functions, it has always been focused on analyzing the output and describing it with the input. But what if we need to do it the other way around? That's where this lesson comes in. We're going to be talking all about inverses. In short, an inverse swaps the input and the output of a function. This is super useful if we need to work backwards from an output that we already know to its input, to reverse a relationship, like turning Fahrenheit into Celsius instead of Celsius into Fahrenheit, or to analyze and describe graph characteristics using output intervals instead of input intervals. Basically, we use inverses anytime we need to input outputs and output inputs. The easiest way to understand inverses is by seeing some. Here's a basic linear function, and here are some of its points. To find the inverse of this function, we literally swap the inputs and the outputs. 0, negative 4 becomes negative 4, 0. 1, negative 1 becomes negative 1, 1. Because the input and the output for the point 2, 2 are the same, the inverse will also stay the same. And finally, 3, 5 becomes 5, 3. Now that we've got a few points, we have an idea of what the inverse graph will look like this. As you can see, it's very easy to find an inverse graphically. What's super interesting is the relationship between these two lines. They're mirror images of each other over the line y equals x. One of the easiest ways to see if two functions are inverses is to graph y equals x and see if the functions are reflections. Here's a new function. But what does that mean? If it was just regular old f of 2, we would just find the point where the input is 2. But that negative 1 exponent is read as the inverse. So this is actually asking us to find the inverse of f with an input of 2. Let's find the inverse by swapping the coordinates in these points. When we're done, the inverse will look just like this graph, but flipped over the line y equals x. The point 0, 4 swaps to 4, 0. 1, 2 swaps to 2, 1. 2, 0 becomes 0, 2. 3, negative 2 becomes negative 2, 3. And 4, negative 4 becomes negative 4, 4. Now that we've got these points, we can draw the inverse line. Now all we need to do is find what this inverse function outputs when you input 2. When the input is 2, the inverse of f outputs 1. One thing to notice about this example is that we could have taken a shortcut here. All we really needed was this one point on the original function. When we say that the input and the output swap, we mean that literally. On the original function, this point tells us that f of 1 equals 2. So when we're worried about the inverse, we just swap the input and the output. 2 becomes the input and 1 becomes the output. So we could have figured out what the inverse of f with an input of 2 was without ever needing to actually graph the inverse. This is a really easy shortcut when you only need to find the inverse of a single input. Let's try another one using that shortcut. This time, we want to evaluate the inverse at an input of negative 3. In other words, we want to find where the original function has an output of negative 3. So where on this graph is this output, negative 3? At this point, right here, where the input is 4. And if the input of the original is 4, then the inverse swaps that over to the output. And just like that, we have our answer. If the original has an output of negative 3 when the input is 4, then the inverse has an output of 4 when the input is negative 3. Evaluating inverses using a graph is as easy as looking for which input goes with a certain output. But it can still be tricky until you get the hang of it. You can practice on our website. In the next video, we're going to be learning how to manipulate function expressions to turn them into their own inverses. See you then.